So today we are continuing with propositional logic. So we'll be looking at precedency, precedency of logical operators. Precedency of logical operators. So the most important thing here is to know, if we are given a compound proposition, is to know which operator to apply first in order to simplify that compound proposition. So precedency of logic operators is to decide which operator to be evaluated first, which operator to be evaluated first, is to decide on which operator should be evaluated first. So what we normally use, we use the precedency table. We use the precedency table to help us know which operator to evaluate first. So with our precedency table, we have the operator, the name of the operator. This is the symbol. Let me just say we have the symbol. This is the symbol of the operator, the name of the operator, and then the weight of, there's the precedency. So with this table, we have the negation operator. It's 1. We have the conjunction. We have the conjunction, which is 2. We have the disjunction, which is 3. And we also have implication. We also have the implication, which we represent. We also have the implication. It's 4. And then lastly we have the biconditional implication. This one is 5. So this is the precedence table that you are going to use throughout this topic. If you are given a compound proposition, and it contains several logic operators. So you start, if there's a negation, you first prioritize the negation, followed by the conjunction, disjunction, implication, and then lastly the biconditional. So let's look at an example where we can try to simplify a compound proposition using the precedency table. So let's say, we have the first example. We are given a compound proposition. Whereby P implies that Q and negation of P. So this is a compound proposition, but we want to simplify it using the precedency table. So first of all, we can see here that the first thing, we can see that we have the negation, we have the negation of the conjunction, and we also have implication, right? So which operator do we start with first? And from the precedency table, we see that we are going to start with the negation, right? So now we need to work with the negation. So if P is equals to true and Q is equals to false. So, okay, these are the conditions. So now the negation of PP, the nature of P is true. So if we take the negation of P, which means P will be false, isn't it? So now we have P implies Q and false, right? So now we have simplified this, right? So if now we have P implies Q to be false, now which operator do we evaluate next? It's going to be the conjunction according to the precedency table. It's going to be this conjunction, and when we are looking at this conjunction, Q and false. So remember what we said about the conjunction. We said with the conjunction is true only if both statements are true, but one of the statements is true and the other is false. So this entire conjunction is going to be what? This is going to be this entire statement is going to be false, because when you are looking at the conjunction operator, we said true is going to be true only when both statements are true, but there's only one statement here which is true, and the other one is false. So this entire statement is going to be false. So now we have P implies F, right? And obviously P, which is true, doesn't imply what? False. So this entire statement is false. So now we have broken down this entire compound proposition to false to see whether it's true or false, and we can see that it's false by using the precedency table. So this is a typical questions that where you have to evaluate a compound proposition using the precedency table. So now we are going to look at two most in common principles which are applied when we are trying to also simplify a compound proposition. So we are going to look at tautology and contradiction. Tautology and contradiction. We have tautology and contradiction. So what is tautology? Tautology, we are saying tautology, this is a statement or a proposition. This is the statement or a proposition that is always true. A statement or proposition that is always true, represented with T. And just to make an example, we are saying P or not P. This statement is always true, isn't it? This statement is always true. And if you remember, this is the disjunction, and we say that with the disjunction, it's only true if at least one statement is true, and this statement is true, right? As much as there's the negation of that statement, but one of the statements is true. So the entire statement is going to always be true. So this is an example of a tautological statement. And basically, when we are looking at tautology, we are saying it expresses a logical truth. Expresses a logical truth. And this means something something that cannot be false under any condition. It cannot be false under any condition. It's always true. And if we can evaluate tautology using the truth table, let's say you have your truth table. Truth table are actually tools that it's a good tool to evaluate any problem that you're given, especially in this topic. So we have 1, 2, 3. Okay, so small letter T will represent a tautological statement, and then P will be a proposition, and we are saying T O P, right? When you're looking at the disjunction operator, using the disjunction operator. So we want to evaluate the tautological statement with the proposition. And so with the tautological statement, we know that it's always true, but the proposition can be true or false, isn't it? So remember, we are using the disjunction operator, and we are saying with the disjunction operator is always true when at least one of the statements is true. So here we have both of the statements are true, which this is going to be true, right? And then the second one, we have at least one of the statements is true, which means this is going to be true also. So this is one way of evaluating the tautology. And we can see that using this condition, it can be true when we are taking a true logical statement and just any proposition, right? So we're getting true. And then now let's look at another principle, which is contradiction. What is contradiction? Contradiction, this is a statement that is always false. This is a statement that is always false. The statement that is always false, we can represent it using small letter C. So e.g., let's make an example of a statement that is always false. E.g., we can have that P and negation P, right? This is always false, isn't it? It's always false. Why is it always false? Because when you're looking at conjunction, we are saying true only if both statements are true. But this statement, they're not both true. One of them is true. So that's why we are saying the entire statement is false. So with contradiction, we can also evaluate it using the truth table, whereby we have a contradiction statement, and then you have a proposition, and then we're using the contradiction statements and the proposition, we're using the conjunction operator. And then obviously the contradiction statement is always false, and then the proposition statements can be true or false. And if we are using the conjunction operator, we are saying it's only true if both statements are true. But here, only one of the statements is true, which is this one. So this is going to be false. And here, only both of these statements are false. So this is going to be what? It's going to be false also. So this is how we can evaluate the contradiction principle using the truth table. The truth table. It's the truth table. Okay, so now we are going to look at the logic laws. These are basic arithmetic laws that we are applying using logics, and also these are laws that we have seen under set theory. So we are going to say let P be a statement, let P be a statement or a proposition, and T, capital letter T, will represent a tautological statement. A tautological statement. Okay, so the first law, we are going to look at the identity law. We're going to look at the identity law, which states that the statements and a true logical statement, it's logically equivalent to the statement itself. And we can also use the disconjunction operator, but we are saying the statement or a false statement is logically equivalent to what? To the statement itself. So this is the identity law, which we can also use to simplify a compound proposition. The other law is what we call the domination law. We use the domination law. So the domination law states that with the domination law, a tautological statement or a contradiction statement will dominate when evaluated with a proposition. So we are saying with the domination law, we have P or T. This is logically equivalent to T. So now this tautological statement will dominate. That's why it's logically equivalent to T. Or if we are looking at, so if we are saying P or P and F is logically equivalent to what? It's logically equivalent to F, because F is going to, the contradiction statement is going to dominate, isn't it? So this is the domination law. It's also very important. So if we have, for an example, let's use this example. If you have P or F and Q or T, right? And then we want to evaluate this compound proposition. So first of all, what we're going to do here, we can see that with these statements we can apply the identity law, which is this one. We can apply the identity law, which is this one. So this can be evaluated to what? Can be evaluated to P, and so looking at this one, we can apply the domination law, isn't it? Where Q, we can apply this domination law, this one, where Q or T will be what? will be T, isn't it? And then also now we have simplified these compound statements to these compound statements, and we know that P and T is what? It's also an identity, which is this identity, right? It's also an identity, which this is logically equivalent to what? This is logically equivalent to P. So we have simplified this to what? To this. So instead of writing POF and QOT, we can just write P, which is the proposition. So we have simplified this entire logical statement to just P, right? So that's how you can actually apply these laws to simplify a compound proposition. So let's look at that other law, which is we're looking at double negation. We're looking at double negation. So double negation is relatively easy. This is logically equivalent to P. So if you have double negation, you're just going to get the proposition itself. And the other one, we have the De Morgan's law. So with the De Morgan's law, we have seen it under set theory, and it's relatively the same thing here. So we are saying the negation of P and Q, this is logically equivalent to the negation of P or the negation of Q, and also we are saying the negation of P or Q is logically equivalent to the negation of P and the negation of Q. So this is the De Morgan's law, and we can actually look at an example whereby we are saying the negation of P and the negation of Q, right? We want to simplify this compound proposition. So the first thing we have to evaluate this negation. So we are going to have, if we simplify that, we're going to have the negation of P, right, or the negation of Q, isn't it? So we just applied, from here to here, we applied De Morgan's. So we applied this one, right? So we had this, right? So we simplified it to this. But then we are not finished. We know that at this point we need to apply what's the double negation. We need to apply the double negation, right? So how do you apply the double negation? Double negation of P is going to be P, or double negation of Q is going to be Q. So this is the simplified version of the compound proposition that we are given. So let's look at another law, which is the distributive law. We are looking at the distributive law. With the distributive law, we are saying we have P and Q or R is logically equivalent to P and Q or P and R, right? So let me just make an example of this one. If we are saying we have A, B plus C, this is also equal to A times B plus A times C. So it's the same thing. This is a practical example of the distribution law. So we've distributed these P within these logical statements, as you can see, right? So And this is the first one. Then we also have the second one where we are saying P or Q and R is logically equivalent to P or Q and P or R, still the same thing. So this is a very important law. We also have the absorption law. We also have the absorption law, which state that P and P or Q is logically equivalent to P. And we are saying P or P and Q is logically equivalent to P. So if you are looking at an example for this one, let's say we have double negation of P or okay, let me just use square brackets to make this one simple to evaluate. To make this one simple to evaluate, we are going to have, and then I have P or this and double negation of P, and then close our brackets. We want to simplify this compound proposition. So we can start with this, the negation, right? Also when you're looking at the precedence table. So this is going to be P, or we have P F, and so also with this negation we're going to have what? Oh, sorry, I can just say we're going to have let me just say this is negation of Q. This is negation of Q. So here, if you're double negation of Q is going to be Q, isn't it? So now we have simplified it. And then from here, I hope you can see that from here we can use the identity. We can use from this. We can use the identity law. We can use the identity law, which we spoke about earlier. We can use the identity law, right? This one. We can use this identity law. So we are going to have, so if we simplify this, we are going to have P or P and Q, isn't it? P and Q. So we applied here P or F, P or F, we are going to use this one. Yes, so we're using this identity law. I'm sorry. So P or F is equals to P. So that's why we have this P here. P or F is what? It's P, isn't it? So now from here we can use the absorption law. From here, from this simplified version, we can use the absorption law, right? So we can see that from this statement we can use which one? We can use this one, isn't it? So this is going to be, and then this is going to be P. So this entire logical statement can be simplified to just P. So this is how you apply these statements, these laws. So now we can also look at the commutative law. The commutative law, and with the commutative law we are specifically looking at the conjunction and disconjunction operators. It says P and Q is logically equivalent to Q and P. This is the same thing of saying, let me example, A times B is equals to B times A. this is the commutative law. If you swap the order of A and B, is still the same thing. You can still get the same thing when you're using this operator. So, and we can also say P or Q is logically equivalent to Q or P. And we also have the associative law. We also have the associative law. We are still looking at the conjunction and the disconjunction operator. The associative law says P and Q and R is logically equivalent to P and Q and R. And then also we can use P or Q or R is logically equivalent to P or Q or R. Same thing if you have A times B times C. This is the same thing as A times B times C. So this is the associative law. And then also, lastly, we can have the inverse law. With the inverse law, we have P and negation of P. This is false. And then P or the negation of P is logically equivalent to true. So these are the logic laws that you're supposed to know, and you can use them to simplify compound conjunction. So these are the most important things that I wanted to cover in this video, and we are going to do a lot of questions based on these and to see how we can apply them. So thank you for